So the first topic that we discuss in Chemistry 163 is kinetics, which is concerned with the rate of chemical reactions. So where we left off in Chemistry 162 was talking about what makes a reaction spontaneous or non-spontaneous. And a good example of a spontaneous process is the combustion of gasoline. And this reaction occurs really quick. You can try this if you like and, pour some gasoline on the ground and set fire to it, and you'll see that this reaction occurs very, very fast. However, if we think about the production of gasoline, which is a fossil fuel, other examples would be oil, gas, and coal, then the production of gasoline in our natural world occurs over a timescale of millions of years. And we see that we can recognize pretty quickly that consumption of fossil fuels is occurring much quicker than what their production is. So the net result of that is that the amount of these things has to be decreasing because we are using them up quicker than what they are being formed. So you recognize fairly quickly that it is important to consider the rates of chemical reactions along with all of the other things that we like to take notice of. So if you want to really understand a chemical system, you need to know a whole bunch of stuff. It would be important to know what the identity is of the reactants of products. It's important to know the ratios in which things are reacting and are being produced, what we call the stoichiometry of a chemical reaction. It's important to know about the energy that is being absorbed or being released during the chemical process. And it's also important to know about the entropy or spontaneity of the process. That's going to tell you whether you need to put energy in order to keep the process occurring or whether it will occur spontaneously. And the focus of this chapter is to study what we call the chemical kinetics of reactions, that is, how fast are they occurring. Now, chemical reactions can occur very, very quickly on a scale of nanoseconds or microseconds, or they can occur very, very slowly, sometimes on a scale of even billions of years. So an important reaction in the formation of air pollution is the reaction of nitrogen, which is normally inert, with O2 at high temperatures inside automobile engines. And what this forms is a substance called nitrogen monoxide or nitrogen oxide, which is an air pollutant, it's an irritant to your lungs. Now, we can talk about the rate of formation of the product of this reaction like so. So the rate of formation of nitrogen oxide will be equal to the change, that's what the delta there indicates, in the concentration of NO. So in chemistry, we use square brackets to indicate the concentration of a substance in moles per liter. And then that is then divided by the change in time. So whenever we're doing the delta of something, we're always going to do the final value minus the initial value. When you enter this into your calculator, whenever you've got a plus or minus sign on either line of a fraction like that, you want to make certain that those terms are inside parentheses. Now, we always express the rates of reactions in chemistry as a positive number. So this is kind of a little interesting when I go to look at the rate of change in the concentration of a reactant. So reactants are going to get consumed during our chemical reaction. And so what we're going to say is that the rate of the consumption of our first reactant N2 here is equal to minus delta NT over delta T. And I'll explain why we need the minus sign here. So we're looking at keeping our reaction rates as positive numbers, and the final concentration of a reactant is always going to be smaller than the initial amount because the reactant is getting consumed. So if we didn't have the minus sign there, this would end up being a negative number. And again, when you put this into your calculator, make certain that you put those terms inside parentheses. Similarly, for the rate of consumption of our other reactant, O2, again, we have the negative of the change in concentration of O2 over the change in time, and then again, it's always the final value minus the initial value whenever we're calculating a delta. So for a consumption, we have the minus sign of a reactant. We always have the minus sign there. Okay, and that's just because we have the convention that reaction rates are always expressed as positive numbers. Now, if you look at this reaction for the formation of NO, what you can recognize fairly quickly is that the NO is going to be produced at twice the rate that the reactants are consumed. So every time I consume 1 mole of that guy, I make 2 moles of this guy. So if I'm using up 1 mole of N2 every second, I'm going to be making 2 moles of NO every second. So the rate of consumption of N2 will be equal to the rate of consumption of O2, because these guys have the same coefficient. Every time I use a mole of this up, I use a mole of this guy, but that will be equal to 1/2 the rate of production of NO. So if this was 1 mole per second and this was 1 mole per second, then the rate of production of NO would be 2 moles per second. It's a little weird writing on the screen with one of these styluses, so you'll see me make the occasional error. Perhaps I'll get better as time goes on. Okay, so in a general sense, I've got this hypothetical reaction here, and I've indicated the reaction coefficients with lowercase letters and the identity of the products with uppercase letters. Then this is how the rate of consumption of the reactants are related to each other, and also the rate of formation of the products. So for a reactant, it's going to be the negative of the reaction of 1 over the reaction coefficient times by the change in concentration of that reactant divided by the change in time, and that's going to be the same for each of my reactants. So the negative of 1 over the reaction coefficient multiplied by the change in the concentration of that species over the change in time. For the products, it's the same, 1 over the reaction coefficient multiplied by the change in concentration of the species over the change in time, but I don't need the minus sign there to keep everything straight. And that's going to be true for each of the products. So let's look at a real reaction now and a real example problem. So it says the oxidation of carbon monoxide to carbon dioxide occurs as below. 2 carbon monoxides react with 1 O2 to form 2 carbon dioxide. And so then it says which reactant is consumed at the greatest rate. So if I look here, if I was consuming O2 at a rate of 1 mole per second, then I would be consuming CO at a rate of 2 moles per second, because for every 1 O2 I need to be using up 2 COs. So a CO is going to be consumed at twice the rate as O2. So now it asks, how is the rate of change in the concentration of CO2, remember what the square brackets mean there, related to the change in the concentration of O2? So if O2 was changing at 1 mole per second, so decreasing, then CO2 would be increasing at 2 moles per second. Now that doesn't really answer the question, but it allows us to see what is going on. How we're going to formally answer the question is like this. The negative of the change in the concentration of O2 over the change in time is equal to 1 on the reaction coefficient of CO2 times by the change in concentration over the change in time. So because this is 1, I didn't need to write the full expression for the rate of consumption of O2, because that's just kind of equal to 1. All right, so that's kind of doing it symbolically. What about doing it with some real numbers? So here we have a hypothetical reaction, really common in online classes to give hypothetical reactions, so you can't Google the data. And it says when the concentration of B is decreasing at 0.5 moles per liter per second, how fast is the concentration of A decreasing? Well, you probably can sort of recognize that if I was using up 2 moles per second of that guy, then I would be using up 1 mole per second of this guy. So the glib answer is, well, it's going to be used up half as quickly. So I'm going to go through the whole algebra though here. So the rate of consumption of B is equal to 0.5 moles per liter per second. And then the rate of consumption of A, the coefficient there is just 1, so go back here. It's really kind of this that we're writing, is equal to negative of 1 on the coefficient of the change in concentration of B per time, and we know that the negative of the change of concentration of B over the change in time is equal to 0.5, so that's just going to be equal to 1/2 times 0.5, which is 0.25 moles per liter per second. So it's pretty simple. If you kind of get a little bit confused with the minus signs, don't worry about it. Just remember that reaction rates are always expressed as positive numbers, and use your sort of intuition there. Okay. Here's one where we're given the relationship between the rates of reactions of a reaction, and we're asked to try and figure out what the balanced reaction is. So it says that the relationship between the reaction rates of a system is found to be, and what I'm always looking for here is what are the reactants and what are the products. And what I know is that the reactants are always going to have minus signs out the front there. So methane is a reactant and O2 is a reactant. The products of this reaction are water and carbon dioxide, and you can see that they don't have a minus sign out the front of their rate expression. Okay, so now we want to figure out the coefficients. This is just 1, so 1 on 1, and they haven't written that in, so that's just 1. But for O2 it's 1 on 2, which tells me that there are 2 of these guys. For water it's 1 on 2, that tells me that there are 2 waters. And for carbon dioxide, there's no coefficient at the front there. That tells me that there's just 1 of those. And if I look at that, it's balanced. And so there I am. There's my balanced equation. 1 methane, 2 oxygens. I recognize they were the reactants because of the minus signs in the rate expressions. 2 waters, 1 CO2. I recognize these were the products because they did not have a minus sign in their rate expression. And then the coefficients I got from these coefficients that are at the front of the rate expression there. Okay, so that's pretty straightforward, I think. So here's another one. It says consider the following reaction. This is another reaction that occurs when we're forming air pollution. So that NO that was formed previously is now reacting with O2. They're reacting in a 2:1 ratio to form 2NO2. This is if the rate of consumption of O2 is 0.022 moles per liter, what is the rate of formation of NO2? So I can see that if I was making 1 mole per second of that guy, I'd be making 2 moles per second of that one. So fairly quickly I can see that it's going to be double. Now, you know, if I can't eyeball it in that way, I can always do the algebra. So from my balanced equation, I know that the rate of consumption of O2 will be equal to 1/2 times the rate of production of NO2. And that's going to be equal to 0.022. So I just got to bring this guy over here. The rate of production of NO2 is equal to 2 times the rate of consumption of O2, and so there's my answer there, 0.044. Alright, so now we're going to kind of look at a few curves of concentration versus time, and we're going to look at these curves quite a bit in this chapter. So we're going back to our first reaction, which is forming NO from N2 and O2, and we know that this is in a ratio of 1 to 1 to 2. So these guys are going to be consumed at the same rate, and this guy here is going to be produced twice as quickly as N2 and O2 are consumed. So the blue curve indicates the consumption of N2 and O2, and we can see that over time the amounts of those things decreases, and they decrease at the same rate. The red curve indicates the rate of formation of NO, and we can see that it increases in concentration a lot quicker than what O2 and N2 decrease. So if I wanted to calculate the rate of the reaction, it's going to be the change in NO, that would be the change in the Y on this curve, over the change in time, which would be the change in X. And what do we call the change in Y over the change in X? We call that the slope. So the rate of production of NO is just equal to the slope of this curve of concentration against time. And what we see when we look at the slope of this curve is that it's very steep near time equals 0, and it's less steep as time passes. So the key thing here is the rate of the reaction changes as time progresses. It becomes slower as time goes on, which is kind of complicate things, isn't it? Okay, so one way that we will talk about the rate, because we have to be very clear how we define the rate because it's going to change over time, is as the average rate between two time points. So this would be an example of using one of these curves to calculate the average rate between two time points. So in this example, what we're going to do is we're going to calculate the average rate for the formation of NO, so we're focusing on the red curve, between 5 microseconds and 10 microseconds. So what we need is we need the concentration of NO at 10 microseconds, that's our final state, minus the concentration of NO at 5 microseconds over our final time, which is 10 minus microseconds. Let's just put it as 10 minus our initial time. So we'd need either a graph or a little table, and we'd have to find those values. So we need NO, because we're trying to look at the formation of NO at 5 microseconds and at 10 microseconds, and that's the data that we're going to use. Okay, so here we go. So the change in NO over the change in time, and again I want to urge you to put that in parentheses. The final concentration, which is at 10 microseconds, 14.8, minus the initial concentration, which is at 5 microseconds, which was 7.8, divided by the difference between the final time, which was 10 microseconds, minus the initial time, which was 5 microseconds. So that's going to be just 5 microseconds. And then I do the math, and I have to think about the units here. These concentrations were given in micromoles per liter. These times were given in microseconds. So it turns out that the micros cancel out, and my final answer, 1.4 moles per liter per second. So that's the format, and you see it's a positive number. If you got some things switched around, you'd end up with a negative number, and you'd need to express it as a positive number. Okay, that's it. So we're really kind of calculating the slope between this point and this point. Now it's going to be an approximation of the rate, because you can see that the rate is changing over that period. you can calculate the average rate over a long time period, and that's an interesting thing to do. We're going to calculate it now between 5 microseconds and 15 microseconds. So what you see is, as the reaction progresses, this line becomes less steep. So when we expand the time period out to all the way out to 15 microseconds, we would expect to get a smaller average rate than what we got before. So let's see what we get. So our two data points are going to be 5, that's our initial, and 15. We want NO, 5 and 15. If you're given a table like this, make sure you don't pick numbers from the wrong column. We're focusing on the formation of NO here. And I'm expecting a smaller number than what I got before. So it's my final value for the concentration of NO, which is 18.6, minus my initial value for the concentration of NO, which was 7.8, divided by my final time, which was 15 microseconds, minus my initial time, 5 microseconds. And I remember to kind of keep these guys in parentheses when I'm entering that into my calculator. Again, the micros are going to cancel out, leaving me with the correct units, and sure enough, it's smaller than what I got before. Before I had 1.4 moles per liter per second, and over the longer time period, I get a smaller number. So kind of, it's logical. And if I went out to even longer time periods, maybe if I went out all the way to 30 microseconds, that average rate would get shorter and shorter and shorter. Now, this gets kind of fun. You can also determine the rate at a particular instant in time. This is called the instantaneous rate of a reaction. And this is a little tricky to do. You have to do it what we call graphically. You've done similar things in Chemistry 162. What you have to do is draw up your concentration versus time chart, and you're going to need at least a couple of points either side of your point of interest, and then you have to draw in a tangent line at that point of interest and calculate the slope of that tangent line by picking 2 points on it. So it's quite an involved process, and if you're doing it on a pen and paper test, you're going to need a ruler, and I'll probably provide you with the chart, and then you just have to draw in your tangent line. So it's definitely a little bit of work and slightly awkward, and you probably want to think about your strategy for tackling problems of this type. So the instantaneous rate of reaction, just a little word of warning, it's quite awkward to determine. And so I would suggest practicing. You'll probably get like one of these on the final. And like I said, you'll be given the chart, but you'll have to draw in your own tangent lines and figure out the slope of that. So what you need is, you don't need to plot necessarily all of the data that's given, but you need a few points either side of the time that you're interested in. And then you've got to draw the tangent line to those collection of points and figure out its slope. And remember, just the slope is just y step over x step. So here we go. We always plot concentration against time. And so this is my point of interest in here at 2000 microseconds. Or 2000 seconds, sorry, in this case. And then I've got 2 points either side. Or actually, I've got just a couple of points either side, and just enough to be able to draw in my tangent line here. And then I just pick 2 convenient points on my tangent line, and I can calculate my slope. And so the rate of consumption of O2 in this case, it's going to be my final value minus my initial value divided by my final time minus my initial time. And then that's going to give me my instantaneous rate, at least an approximation of it at that particular times point. Okay, so I just want to point out here, as I was going through that, I was kind of like, oh, I slowed down a little bit. Because we've got this minus sign in here, you can see that I just flipped the order of these things. That's not so important, as long as you are consistent that these go together. So this concentration goes with this time, this concentration goes with this time. The math will all work out in the end, and the important thing is that that has to be a positive number.